Okay, and understanding what work is basically a potential. So I'm going to focus on work, and we'll be discussing the different varieties of work. Work, I want you to think of work as a potential, and it's going to help you immensely, well beyond this class, because people use that term all the time. I know it took me about 20 years to figure out what they meant by this, and that just basically means work. My ability to do work or to have work done on me has got to do with some sort of a potential. Okay, so we discussed the idea of work as being something useful to us, something that we define as useful. Things can do work that is useless, and that's where enthalpy comes in. We dump all the useless work into that. But basically, think of anything that's useful as work. Okay? If you look at the physics definition of work, it's the integral of some sort of an external force dotted with some sort of surface, and that's going to give you the work. This is the most general kind of definition for work. And then if you've taken some sort of a physics class that didn't even have any calculus in it at all, which is completely possible, you may have seen that people said that work is equal to force times distance. It's not cross, it's times distance. And so what that would mean is, for example, I'm taking this marker and I'm moving with it, and I put it here. I put work into moving it from this distance to this distance. That's kind of what people usually mean, and you may have seen that if you took some physics course, and that's kind of how they describe it. Something was pushed and it went from this distance to that distance, how much work was done, or how much work did it do. That kind of thing. So that gives you an idea for what work is in a very general way, but there are a variety of different types of work you could think of that for systems for us to do. And there's a whole list of those things, but I want you to think of them all as potential. Okay? So when I was describing this whole idea of this cell phone running out of battery, okay, then I plug it into the wall. Before it, when it's at 100%, it has the highest potential to do something. Okay? It has some sort of a drive to do it, and it will do that, and it will execute that and eventually deplete itself. Okay? That is known as an electrical potential, or electrochemical potential, and that is an ability to do work. A sociological type thing to think about is the potential of a brain to execute something. So for example, if someone told you as a kid, oh, you got a lot of potential. What does it mean? I mean, it means literally this. It means that in and of itself, to your own volition, you will be able to do well. You will be able to excel, provided everything follows. And you have the drive, the ability, whatever it is, to go on forward. So you have what we would say is work is greater than 0 at that point. Okay? That's what we mean in that potential sense. Okay? So as you are executing your plans to become, I don't know, a neurosurgeon or the President of the United States or whatever that is, you are executing work, you're doing something useful for society, you have a W that's greater than 0. Okay? So contrast that with someone who has no potential. Okay? So people say that too, from a sociological point of view. They say, oh, he has no potential. So what that would mean is that, to that person at least, they surmise that this person that they're talking about is sort of useless to society, and they're just, a burden to society, etc. Whatever they define that to be. And that would mean, in that sense, and I'm being very general to show you that thermodynamics has implications beyond just the physics and chemistry of it. And you could think about analogies beyond this class in the sociological term. I am not making any generalization as far as sociology goes. I'm just explaining things in ways that people discuss these terms. People usually say, he has no potential, or she has a lot of potential, whatever. I'm just explaining it in understanding this idea of potential. If someone has no potential, we say that they're kind of useless. If we want them to have potential, we have to educate them, we have to provide food for them, whatever it is, to rehabilitate them until they get to a point where we as a society say that now they could do something useful. Do you see how the whole thing is very subjective? Okay? That is exactly the same way in physics and chemistry. It's extraordinarily subjective. One system to one person could do useful work, and to another person they'd say, I don't care for that, that's useless work, and they dump it into the enthalpy. Whatever that is, we define what useful means, what useless means, and this potential, the idea for potential. But it gives you an idea for directionality to some degree. So when I have a dead battery on my cell phone, okay, then it has no more potential. It reached, so my 0% battery, that means work is 0. It cannot do work. I did not put work into it. It reached a final state. It's dead now. Now, if I wanted to do work, I have to put energy into that to restore it back to 100%. I have to put work is negative. I have to put work into that, and then when it goes back to 0%, it is doing work. But once it's at 0, it's going to be at it has no potential. It has no work. So when I say work is 0, what it would mean is that I've reached some sort of an equilibrated state where nothing is occurring and it has no potential to go one way or the other. So when I'm talking about a marker falling to the ground, well, it fell to the ground, now it can no longer fall, it has no potential, it's stuck, it's got work of 0. Whereas up here I can define a potential work for it to fall, and I have something that would have a positive ability to do work for me. That's what we mean by this, okay? We could think about it from the point of view of a spring, and we'll get to that too. When I compress a spring, at that point, it has the ability to do work for me. So it's sort of like a charged battery. And then as soon as I release my hand, it will doing until it reaches back to where it used to be. But while it's doing the doing, I can have something attached to it. Maybe it's some sort of mechanical contraption that it's like a little toy that moves. Maybe it's pushing back against a person trying to sleep, and then when it comes back it decompresses. Whatever it is that I'm trying to do and define as work is basically my own subjective reference frame for what I want to define as positive, what I want to define as negative. And by and large, society agrees with most of the things, and we have established conventions. For example, for batteries, what that would mean, and for other things as well. So let me now explain to you this whole idea of potential and work with specific examples. And after we discuss the second law of thermodynamics, I will be able to show you, and watch out for that video as well, an auxiliary function we call a free energy that tells you the maximum work it can derive out of a system. And there are two types of free energies that people usually talk about, and they come out of this idea of work. I have stored work to do something. Okay, so we have two very general things that we'll discuss later. At this moment, don't worry about it, but I want to discuss these potentials and these types of work. So one very, very important one is expansion contraction, which is also known as PdV work. And it's known as PdV work because that's how it's defined. That's the work of expansion and contraction. Usually that would mean a compressible substance like a gas. So a balloon a limp balloon that I'm putting work into it, it's expanding as I'm blowing air into it. It's going to expand, and it could do something for me while it's expanding. A piston cylinder device, where I showed you before, where I have a device here that's going to make this thing move up. Okay, this I can measure the work using this equation. Work will be equal to PdV. Okay, and so from a practical point of view, V here is volume. It's going to go from volume of 1 to volume of 2. We will discuss a lot of other ways to do this, but one way is if I say if for constant pressure, and that's a very specific scenario when pressure is constant, usually isn't, then I can pull this out of the integral and I get that work is equal to P delta V, meaning P is equal to V2 minus V1, V is volume, P is pressure. I can do that, but only when pressure is constant. There's a whole variety of different simplifications you could use for this. We will discuss this to death, and you will know a whole lot about this in greater detail about expansion-contraction work. It's a very, very important type of work for people in the mechanical field when discussing engine design, or people in the chemical field in explaining some types of reactions and how they will expand and contract. Among other things you could do with expansion contraction. So we in thermo often look to expansion contraction as a natural sort of way to explain things, because a lot of the mechanical systems and the chemical systems that came out of the 1900s and the 1800s, and the 1900s were based on the early work of the people that came up with thermodynamics and coalesced it. So we have PdV work taking a prominent role in the equations that we use. And rightfully so, because a lot of our devices, like a turbine or a fan or whatever that is, very much rely on the idea of PdV work. So many engineering majors and disciplines heavily rely on that. But that's not the only way to do it. So let's look at other ways. I could have, for example, have my system here, some sort of a box where I have something that I want to happen. I can hook up a circuit into this thing, put a resistor here, resistor in there, and I can put this into anode cathode type thing, and I can have current travel from positive to negative, and it will go this way. And the only way for this to occur is if I have a voltage difference, and I'm making this squiggly V to differentiate that from volume. So I have this squiggly V for voltage. The voltage difference is the voltage, kind of like an electrical potential. When I have this as a positive, it is able to move that current around. When I don't, when it's zero, it won't. It will stop, the battery's dead, I have to recharge it. So we're going to basically discuss this idea of an electrical potential by hooking these ideas together. So if I want to know how much energy I'm putting into the system, what I need to do is figure and measure the time, the length of time that it took for me to go from this point to this point. Okay, so if let's say I want to know how much work was given to my system over a 10-second period, delta T would be 10 seconds, and what I could do is to get the work, the electrical work would be VI delta T. Okay, V being the squiggly V for voltage, I is the current, and delta T would be time, the change in time. Okay, this is a very generalized, simplified way to look at it. You could look at it as basically work is equal to the integral of VI dt from T1 to T2. That's kind of the most generalized form to figure that out. And then I just assume that the voltage and the current are independent of time. They often are not. So if you take an electrical circuit type course, there's ample discussion here with Kirchhoff's law and all the other things that you do in explaining how these two terms may interplay together to get you the work, the electrical work. And you can think of this as an electrical potential energy. When this potential energy is zero, I have no ability to do anything anymore. And my electrochemical cell is kind of dead and I can't do anything. And when it's not, then it can. When I plug this contraption into the wall, it is able to do work for me because I'm providing work to it. Okay, I'm providing some sort of a charge buildup, and it will be able to do that. When I charge the battery of a laptop, I put some energy into a capacitor, which can then discharge and have a voltage difference and do this kind of stuff. Okay, so this could be something like a toaster, and I'm toasting bread, and my system is the slice of bread and a toaster that I'm toasting it in, and I'm trying to understand the efficiency of the toaster. It could be like a cup of water that I'm trying to heat up, whatever it is I want to do, or it could be a chip where I'm trying to create an electrical flow so that I can store some sort of data, like this video, on some server somewhere in California so you can see it wherever you are on YouTube. Whatever that is, this gives you the idea and an understanding of how the potential would work. And when I get to the potential of zero, nothing's happening. I reached a state of equilibrium, and I have no more ability to do it. Is surface work, and basically, let's say I have this surface of water or something and I want to expand it like that. Okay, the work required in changing the area is proportional to the surface tension. This is known as surface work. So people do this when they're trying to expand an area of something. So maybe you're blowing a balloon underwater, and as you're doing that, you're expanding the area of the balloon against its own surface tension, and you can discuss the work that you're doing. As far as that goes, the surface work that goes into that. And if you're doing anything with surface science, like nanotechnology or anything like that, you will be discussing that, that potential. These are all potentials, as I mentioned. When the work is zero, they cannot not do it. And you have a directionality to it. They will all tend to go to zero when they have a positive, and when they have a negative, you need to provide work into it in order for it to be done.